The purpose of this video is to show how to build with the Python library pytorch a deep learning model to do handwritten digit recognition. I'll firstly show you some applications and later I'll go through an explanatory notebook on how to download the dataset, build, train and evaluate a convolutional neural network model. In the description you will find the GitHub page of the notebook with the code used in this video. This is starting notebook to learn how to build a neural network model to do handwritten digit recognition. You can find in the description some resources used to write the notebook. Let's import all the needed libraries for this notebook. After that we need to detect the available device on the laptop. If CUDA is available you're going to use the GPU, otherwise we will use CPU. By using CPU, the training time is going to increase. The availability of GPU depends from your machine. Define the base path of our data. Define a transform operation that is going to be applied on each downloaded image. The transformation consists in converting the image to tensor and apply a normalization. Download train and validation sets from the famous NIST dataset. This is a famous dataset containing handwritten digits. In the next cell, we're going to use dataLoader function. This function combines a dataset and a sampler, and provides an iterable over the given dataset. These iterables will help us to iterate over the training and validation sets. Let's print dimensions of images and labels. Let's display one random image. In the next cell, we're going to build our CNN model. CNN stands for Convolutional Neural Network. When building a neural network model in PyTorch, we need to inherit the NN module class and to re-implement the constructor to build our custom network with its layers. We also need to re-implement the forward method that will be used in the forward step in the neural network training. Let's create our model. We need to move to the device. This step is not necessary if we're using CPU, but it is needed on the opposite if you're using GPU. We need to define the loss function to be used as well as the optimizer. We can define the number of epochs, but before it is important to precise the meaning of epochs, iterations, and batch size. One epoch is when an entire dataset is passed forward and backward through the neural network only once. The total number of training examples present in a single batch represents the batch size. The iterations is the number of batches needed to complete one epoch. In the next cell, we're going to define a train function that we will use to train our model. It takes as input the model to train, the optimizer, the loss function, the number of epochs, the train iterator, the validation iterator. Let's define inside a subfunction to calculate the accuracy. We will use it at the end of each epoch to calculate the train and validation accuracy. For the training during each epoch for each batch, each iteration, we do a forward step with our neural network. This is the purpose of the double for loop in the function. We calculate the loss over this batch with the error function. We calculate gradients and we update parameters thanks to the optimizer with the step function. Every epoch we check for the train accuracy, that is the accuracy measured on the train set. We repeat the same for the validation set without calculating gradients. If the validation accuracy improves, we store the model state. Let's analyze the training results. We can display the train loss for each iteration for both the train and validation set. By showing results after each iteration, it is expected this random behavior, but in next plot per epoch, we will see how we're slowly improving the results. In the graph per epoch, we can see how the model is slowly improving. We trained only for 10 epochs, but we could try more epoch to improve results. Let's recompute the results on the validation set. In the next cells, we're going to define some functions to analyze the results. We can plot the confusion matrix. A confusion matrix is a table that is commonly used to evaluate the performance of a classification model. It provides a summary of the predictions made by the model against the actual labels or classes of the data. For a classification problem with n classes, A confusion matrix will have n rows and n columns, representing the predicted and actual classes, respectively. Each cell in the matrix represents the count or frequency of the data points that belong to a particular combination of predicted and actual classes. In the next cell, we're going to plot a classification report. The classification include for each class the calculation of the precision, recall, and F1 score are commonly used evaluation metrics for classification models. Let's define each of them. Precision. Precision is a metric that measures the proportion of correctly predicted positive instances out of all instances predicted as positive. It focuses on the quality of the positive predictions. The formula to calculate precision is precision equals TP/TP plus FP, where TP represents the true positives, correctly predicted positive instances, and FP represents the false positives, instances predicted as positive but are actually negative. In simple terms, precision tells you how many of the instances predicted as positive are actually positive. A higher precision value indicates fewer false positives, implying that the model is making accurate positive predictions. Recall, also known as sensitivity or true positive rate recall, is a metric that measures the proportion of correctly predicted positive instances out of all actual positive instances. It focuses on the ability of the model to find all positive instances. The formula to calculate recall is recall equals TP/TP plus FN, where TP represents the true positives, correctly predicted positive instances, and FN represents the false negatives, instances predicted as negative but are actually positive. In simple terms, recall tells you how many of the actual positive instances were correctly identified by the model. A higher recall value indicates fewer false negatives, suggesting that the model is capturing a higher proportion of positive instances. F1 score. The F1 score is a harmonic mean of precision and recall, providing a single metric that combines both precision and recall. It is particularly useful when you want to find a balance between precision and recall. The formula to calculate the F1 score is F1 equals 2 asterisk, precision asterisk recall, / precision plus recall. The F1 score ranges from 0 to 1, where 1 represents the best possible value, perfect precision and recall, and 0 represents the worst. The F1 score gives equal importance to precision and recall. It is commonly used when you want to evaluate the model's performance in situations where both false positives and false negatives are equally important. Let's load a model and do predictions over a random image. The model correctly classified the image. The final cell is used to generate a video from the predictions on a small set. I hope you enjoyed this video. For any question you can write me in the comment section. Don't forget to subscribe to this channel.